Okay, so here's a cone. Here's a cone. And it's hollow, and we're going to put some stuff in it in a second, okay? But before I do that, let me tell you some information about it. Yeah, no, unfortunately not. Well, maybe melted ice cream, as you'll see in a second. Okay, so it's a cone. What two measurements do you need to define a cone? You need its height. Okay, so I'm going to tell you it's 5 meters tall. Okay, and its radius. Okay, so radius of the base, right? So I'm going to give that 2 meters. Okay. So there's some fluid in here. So let's draw some fluid in. I'm going to. Yeah, think of how much ice cream this is. This is a lot of ice cream.
Meniscus.
It's like a. It's like a. I suppose it'd be like a factory.
Or ice cream for giants.
Or ice cream for giants. Okay, so here's our cone, all right, and it's actually got a hole at the bottom. Okay. A tiny point-sized hole, okay, so it doesn't actually muck around with the dimensions of our cone, which is convenient. And so things are actually coming out, things are leaving the cone at a rate of 0.2 cubic meters every minute. Yeah, that's what we got. Okay, so if that's how much stuff is coming out, I'm interested in this level of where it's at, okay? That's position there, okay? It's obviously dropping, okay? So my question is, how much is it dropping, that level, okay? And how much is it dropping when that level is actually equal to a certain position? I think the number I've got is, let's see, when there's 4 left. So actually it'd be quite a bit higher, okay? So when that's equal to 4, how quickly is it dropping? Okay, how quickly is it dropping? So I just gave it to you verbally, but a lot of it's on the diagram. How can we set this up? What information have I given you? This is volume over time. Volume over time, right? dV on dt. What are we after? Okay, now, we don't have anything on here, right? So we need to introduce a variable. And if we're after height, okay, a decent name for that would be h. Okay? So I'm after dh on dt when the height's 4. Are we happy with that? Nod at me slowly if you're happy with that. Yeah, okay. None of you should be nodding right now. Ha! Psych. What's wrong? There's something drastically wrong with this. Wow! Things are coming out of my cone and there's more stuff ending up in my cone every minute, okay? So hold on, have a look. What do we write? I said stuff's coming out, but my rate is positive, which means things are increasing, okay? So this is bogus, right? Be careful, okay? This is negative, okay? Now, I'm drawing particular attention to that, right? Because it's a classic error. Very, very easy error to make. Because you just look at the numbers, and you're like, the number's the most important part, and then you go ahead, and all the numbers, like you don't come up with a numerical error until you're at the end, and you're like, what? I'm getting more stuff, even though stuff's coming out. It's breaking the laws of thermodynamics. Anyway, okay, so that's what I've got. That's what I know, all right? Now, before I said, okay, you're going to have this being equal to, and then you need the chain rule over here, right? So it'll be something over something, okay? So I need to have a dh here and a dt here, okay? So therefore, what would you expect is the missing piece? dv. Okay? Now this step is very crucial. It'll become important in a second. Because, what was the thing we did at this point in the previous question? What did we do? Right, so we said, okay, good, I know this bit, it's supplied to me by the question, but I need to know this bit, right? So then you think about, okay, well, what's the equation that relates those two together? Okay, what is the equation that relates those two together? The volume of a cone, which is the third pi r it's a third of the cylinder with the same dimensions. Okay. Now, can anyone see the problem? I guess I want dV on dH, and then I'll flip it, yeah? But I don't just have h in there. I've also got this pesky r guy, right? And you can't ignore him because h obviously is changing, okay? It's getting smaller. But r, what's r? There's no r on my diagram. It's the radius of what? Right. Okay, we sort of said, well, what's this volume? Right? The volume's the green part, and it's changing as we go. It's not the volume of the whole thing, which is static. Okay. Now, if that volume is changing, its height is changing. Obviously, its radius is also changing. That's r, right? So just be careful, right? Because we write an equation like this without thinking. Because you're like, well, obviously there's an r and an h, but what is it? Okay. All right. Now, even knowing what it is, you still got a problem. Okay. Because if you want to differentiate this, I need to have it in terms of one variable, namely the one that I want to differentiate with respect to, h. Okay. So what do? Okay, I need to get rid of this r somehow, okay? But I've got some problems. I can't just put in a number, right? Because the number will change. At some point the number will be 2, and then at some point the number will be 0, and then there's all these different values in between. Okay, so r really is changing. I need some kind of variable in there, right? So what will I do? You've got a couple of options. You could go for Pythagoras if you wanted, because there's a right-angled triangle in here, right, with the perpendicular height. The reason why I don't think that's such a great option to go with is because I don't know what the perpendicular height is. I'm sort of replacing that problem with another one, right? I know what this height is, but it's going to be changing, yes? So, and I'm going to introduce a square root into it, which is a mess. Okay. I think a better option here is seeing that as r and h change, there's actually a really, really simple relationship between them, okay? R and h, because this is a cone, right, are always going to be a kind of cone that's similar to the big cone. Does that make sense? As my cone gets smaller, it's always just going to be a similar version of the original cone, okay? Therefore, I have some similar triangles here, right? Where are the similar triangles? I'm not going to ask for the proof, because this is not a similar triangles proof. It's a related rates proof. It's this one in here, okay, which does happen to be right angle, and this bigger one here, okay, which is also right angle. Okay. So what ratio am I after? Remember what I'm trying to do. I'm trying to get rid of r and replace it with h's, because that's what I'm going to differentiate with respect to in a second. Okay. So what ratio should I put down? I want to get rid of r's, right? So I'm going to make r the subject. So I'm going to start with r. Okay. You know that long thing which you always hate writing in similar triangles proofs about the ratios of sides? What do you actually say? You know, something over something is equal to something over something else because, because what? What's the what? What's in here? Corresponding sides in similar triangles are in the same ratio, right? So which are the corresponding sides? Well, I'd go short side to long side. R over H, okay, should be equal to 2 over 5, short over long. Okay, I suppose I could have written it upside down, but I'm after the R, right? So this makes it easy. I just have to do one thing, kick the H over the other side. Okay, so now I can get my volume in terms of just H. It'll be a third pi. Now what's R squared? It'll be 4h squared on 25. And then I have another h on the end. So tidying that up, I'll get 4h cubed pi. I should have put the pi first, sorry. 4 pi h cubed on 75. Okay? Alright. That was hard work to get to that point, okay? Because I had to recognize that I had a problem here, and then I had to fix the problem. Now what do? Yeah, I set up chain rule before, so I've got all the pieces I need to chuck it into here, okay? Do note that it's dH on dV, not d, sorry, this is v, so I need to know what v on dh is first. Haven't differentiated yet. But thankfully it's a pretty easy function to differentiate, right? What do I get? Yes, this 3 is going to come out the front. Because I know in advance that my denominator is divisible by 3, I'm just going to, rather than make numbers bigger and then make them smaller, I'm just going to make them smaller to begin with, yeah? So this is actually going to be over 25, okay? And this will be 4 pi h squared. Okay, you saw how the 3 came down? Alright, so now I can put this in. It's the reciprocal, so 25 over 4 pi h squared times, here we go, minus 0.2. Minus 0.2. That's minus a fifth. Yes? Okay. So this 5 is going to factor into that 25. So I'm going to get minus 5 over 4 pi h squared. Okay? Now notice, if you'd mucked up and you'd said it's 0.2 cubic meters per minute, a positive value, then at this point you would get a positive value. And that'd be the point where you say, wait, something's gone wrong because my thing's getting taller, not shorter. Okay? So we want it at a particular point now when h is equal to 4. So dh on dt at that point will be minus 5 over 4 times 16 will be 64. And that doesn't factorize, so that's it. Now again, see, here's a really good example of what I'm talking about, because you've got your negative there, right? It's kind of awkward really to say, and people don't talk in this language. They're like, hey, how's the height changing? You're like, well, its rate is minus 5 on 64 pi. You'd say it's going lower, it's descending, right? It's dropping. So I would say the height is decreasing. At 5 over 64 pi, what my units? Meters per minute. So much the same way as we say, oh, lengths have to be positive. Rates tend to be positive as well, but we just supply the direction when we talk about them in natural language. Okay?